All right, everybody. Thanks for tuning in online. Hopefully next class will be in person again. Anyone who is willing to, please turn on your camera just to sort of simulate the in-person experience as much as possible, hopefully. Just as in class, if anything I say is unclear, you can just speak up and ask a question. Online is a poor imitation of the in-person experience, but let's try to make it as interactive as possible. So just to summarize a bit, for the last two lectures, we took a bit of a break from game theory, and we just studied learning. We studied sort of over the series of two lectures, the derivation of this polynomial weights algorithm, which is somehow a way to choose actions in some dynamic sequential environment. And it had some nice properties. The promise was no matter what losses or payoffs were associated with these actions, if you use the polynomial weights algorithm to choose the actions, then you'd have the promise that no matter what happened in hindsight, you, the algorithm, did as well as whatever turned out to be the best action in hindsight. So what I want to do this class is start, and we sort of foreshadowed a little bit that you could use this to play a game. But we didn't really sort of bring it all the way back to sort of game theory. And so what I want to do this class is to start to close that loop. So I want to talk about an important class of games, zero-sum games. And zero-sum games are sort of both interesting and important class of games, but also a very structured class of games. And they've got a very interesting property called the Minimax theorem that helps us both think about how one should play in a zero-sum game and characterize what the equilibria are in zero-sum games. And what we're going to do this class is we're going to prove that theorem. We're going to prove the Minimax theorem. And the proof will turn out to sort of fall very easily out of a thought experiment that comes from sort of thinking to yourself, what would happen if you started to actually play in a zero-sum game using the polynomial weights algorithm? So it turns out that if you play using the polynomial weights algorithm in a zero-sum game, this is something we'll prove next lecture, play actually will converge to Nash equilibria. So we're, so bringing this back to sort of a previous theme in the course, the polynomial weights algorithm will be a sort of plausible learning dynamic for convergence to equilibria in zero-sum games. But more than that, it will help us prove interesting structural properties about the equilibria of zero-sum games that are not true in general sum games. Okay. And so yes, so like the way we're going to use it today is sort of as part of a thought experiment to prove a theorem that von Neumann proved in a very different way 70 years ago. But now that we know about the polynomial weights algorithm, the proof for us is going to be much easier than it was for him. Okay. So let's remember what games are and sort of think specifically about zero-sum games. Let's see. So raised hand, just go ahead. You don't have to raise your hand. You can just unmute.
Sorry, I was just wondering if the slides are posted because I don't see them on the website.
No, they are not yet posted because my VPN was acting up and I can't connect to Penn servers from home. Yeah.
I just wanted to check.
I can post I can post them in the Slack if you want to refer to them right now.
No, that's okay. You can continue. Didn't mean to interrupt. Thank you.
Okay, yeah, they'll be up shortly. Oop. Got a message saying Zoom quit unexpectedly, but it doesn't look like it's quit. Can you guys still hear and see me?
Yes.
Okay. Oh, keeps telling me that it quit unexpectedly now. Yep. All right, now it's restarted on me. Can you guys still hear and see me?
Yes, we can.
Okay. Well, it still seems to be recording. All right, let's share screen again. Okay. So, okay, so what's a two-player zero-sum game? Well, it's just what it sounds like. It's a two-player game such that for every action profile, and in a two-player game, an action profile is just a pair of actions, one for player one and one for player two. For every action profile, the utility that player two gets at that action profile is just the negative of the utility that player one gets. And so the reason these are called zero-sum games is if I sum up the utility of the two players in the action profile, it sums to zero. And one thing you might notice is that there's nothing special about zero. If I added, some constant like 5 to every utility function, that wouldn't change the strategic nature of the game at all. So, we could equally well talk about 5-sum games instead of zero-sum games. The point is just that these games are strictly adversarial. So the only way that player one can change his action to improve his payoff is to harm player two by exactly the same amount and vice versa. So the fact that they sum to zero is not important. The important thing is that the sum of the utility functions is some constant. It doesn't change across action profiles. And what that sort of means strategically is that there's no pie to enlarge. Like any sort of gain for me is met in equal proportion by a loss for you. And one thing we won't talk about too much, but I'll just maybe mention for those that are interested, zero-sum games, and in particular the Minimax theorem that we're going to prove today, are really sort of fundamental objects, not just in game theory, but in computer science and optimization and mathematics and the world broadly, machine learning. And so, if you're interested, there are very, very close connections between zero-sum games and linear programming. The Minimax theorem we're going to prove today is really in a fundamental way the exact same thing as linear programming duality. If you know anything about adversarial machine learning, so GANs and sort of the way people train models for to be sort of robust against adversarial examples, these are solving for the equilibria of very large zero-sum games. Anyways, so sort of beyond the ability for zero-sum games to model strictly adversarial interactions, these are sort of really fundamental objects that you might encounter again and again. But okay, let's sort of start by thinking about zero-sum games just in sort of the simple 2x2 matrix game, anecdotes of economic game theory way that we've used before to think about sort of very simple games. And so here's a simple 2x2 matrix game that is sometimes called the presidential election game. The story is unimportant. We're just going to use this as an example of a simple zero-sum game. But maybe here's the story. There's a presidential election between a Democrat and a Republican. and these are sort of simpler times before campaign issues might have been things like infectious disease and democracy and things. This was back when candidates might choose to focus on relatively mundane things like the economy or the social contract or morality or tax cuts. And the idea for this very simple game is that the two candidates at the beginning of the election have to pick what is the issue, the main issue that they're going to focus their campaign on, and how this issue will, how focus on this issue will play out in the election will depend on what their opponent decides to focus their campaign on. Okay, so maybe depending on what the row candidate picks, to focus on the economy or the social contract, that will induce some odds that they win the election, depending on what the column player chooses to focus on, morality or tax cuts, say, where bigger numbers correspond to a larger chance of winning the election, and smaller numbers correspond to a smaller chance of winning the election. And because it's an election, there's one winner, it's a zero-sum game. The only way I can become more likely to be elected president is if you become less likely to be elected president. Okay, so you can write down a toy little game like this as a 2x2 matrix in the way that we're used to. Now, because it's a zero-sum game, just like notationally, it's a little wasteful to write down payoffs the way we're used to writing them down, right? We're used to sort of writing pairs of numbers in every entry of a matrix like this, one corresponding to the payoff of the row player and the other corresponding to the payoff of the column player. But because this is a zero-sum game and the column player always gets the negative of what the row player does, we can sort of more economically write down just a single number in every entry, the payoff for the row player, which we can now think of as the cost for the column player. So the row player would like to end up in the sort of square of this game matrix that maximizes the payoff. Similarly, the column player would like to end up in the square of this game matrix that minimizes the cost, and the payoff and the cost are the same. So one player is trying to maximize, the other player is trying to minimize. Okay, and so we might as well give our candidates names. Let's call the row player Max, because Max would like to maximize the number in this matrix. He'd like to maximize the utility. And we'll call the column player Min, because Min would like to minimize the number in this matrix. Okay, so I want to think about how one should reason about playing in a zero-sum game, given that their opponent is clever. So let's sort of go through maybe an exercise in reasoning about this, and I'm going to ask you various questions about what people should do. And I don't want you to, do algebraic calculations in your head and give me a number. What I'm looking for is more sort of instructions for how to go about thinking about, instructions for how you might think about computing those numbers, not the numbers themselves. So I want to think about how to play in a zero-sum game, and I'm going to focus first on order of play. So suppose that Max has to go first and announce his strategy. Max's strategy could be randomized. So Max's strategy doesn't have to be, I'm going to center my campaign on the economy. It could be that, Max's strategy as well, with probability 60%, I'm going to center my campaign on the economy, and with probability 40%, I'll center my campaign on the social contract. So the question is, if Max is sort of handicapped and forced to go first and like reveal his strategy to Min, and Min has the advantage of getting to best respond, maybe she has spies on the inside of Max's campaign, she figures out what his strategy is and gets to choose the best response. I want to sort of figure out how Max should think about how to choose his strategy. And maybe to sort of start thinking about this, suppose, there's sort of two optimizations here if Max goes first. Max has to optimize for what's going to happen when Min best responds. And Min best responding is itself an optimization problem. There's this nested optimization. And so let's think about it from the inside out. So suppose Max announces some particular strategy. It's like, he's going to randomize uniformly. So like, half the time Max is going to focus on the economy, half the time he's going to focus on the social contract. What should Min do? And here, I'm not looking for necessarily like which action she should play, but what thought process should she go through to figure out what she should do? Anyone can unmute and answer.
So Min could, say like let her probability of playing morality be alpha. And then once you define that, what her expected utility will be. And so she can just choose alpha to minimize that like expected payoff.
Yeah, and I guess she might know even right off the bat that like whatever, so alpha it's like the probability she's going to play like morality or something, and 1 minus alpha is the probability she's going to play text cuts. Is that what you're saying?
Right.
Yeah, and I guess she would like know right off the bat that alpha was going to be 0 or 1. Like if you're just best responding to something I'm doing, there's no need for you to randomize because your payoff is going to be, if you randomize between two things, your payoff is just going to be the average of the payoffs of the two things you're randomizing between, and the weighted average can't be larger than the maximum of the two things. But like you're exactly right that what Min should do is she should figure out, given what Max is doing, what is the utility of playing each of her two actions? What's her utility for playing morality? What's her utility for playing tax cuts? And she should pick the better of the two. And remember, Min is trying to minimize the utility. So she should write down an expression for her expected costs for playing morality, an expression for her expected costs for playing tax cuts, and she should play whichever of those two is smaller. So, right, she can do that. She can say, look, if Max is uniformly randomizing between these two actions, then if I play morality, half the time I'm gonna get payoff 3, and half the time I'm gonna get payoff -2. And so my expected utility will be half times 3 plus half times -2, which is 1/2. And similarly, she can think to herself, well, if I play tax cuts, if Max is uniformly randomizing, half the time I'm going to get payoff -1, and half the time I'm going to get payoff 1. And so my expected utility is half times -1 plus half times 1, which is 0. And Min is trying to minimize the payoff. And so having gone through this calculation, she should play tax cuts. Right? Like if her best response problem is pretty straightforward, given that she knows Max's strategy. She just, for each of her actions, computes the expected cost of that action, and she chooses the action that minimizes the expected cost. Okay. And we can generalize this, of course, right? Like the particular numbers here were specific to Max announcing this like uniform distribution, 1/2, 1/2 on his two actions, but the basic logic is straightforward no matter what Max announces. So more generally, if Max announces that he's going to play according to some mixed strategy that puts weight P on focus on the economy and weight 1 minus P on focus on society, then what Min should do is she should go ahead and, under Max's distribution, figure out what her expected cost is for playing each of her actions, and then play whichever action minimizes that expected cost. Okay, so we can write that down, right? Like her cost for playing morality, if Max puts weight P on economy, is going to be P times 3 plus 1 minus P times -2. And her payoff for playing text cuts is going to be P times -1 plus 1 minus P times 1. Okay, and she will play the action that minimizes these two expressions, either the expression for her payoff for morality or the expression for her payoff for text cuts. Okay. So if we can work this out, then Max can work this out, right? Like Min and Max are not they're not going to cooperate here because it's a zero-sum game, right? Anything that's good for Min is bad for Max, and so Max knows that this is the logic that Min is going to go through if Max announces some particular strategy. And so the question is, knowing this, what strategy, P1 minus P, should Max announce to maximize his payoff after Min best responds? Right, what should Max do? Again, I'm not looking for like a number, looking for sort of a thought process.
Should he choose a value of P that like maximizes this argument function?
Exactly, right? Like he knows what's going to happen if he plays P1 minus P. If he plays P1 minus P, then the utility that he's going to get is the utility for the action that Min chooses. But he knows that Min is going to choose the action that minimizes the utility between her two choices, right? So, maybe covering up, if I cover it up on my screen with my finger, it doesn't cover it up for you, but covering up the argmax for a moment. Max knows that if he plays some strategy P, then the utility he's going to get is whichever is smaller, 3P minus 2 times 1 minus P, or P times -1 plus 1 minus P. And so since he wants to maximize that, he should play the action, he should play the distribution P that maximizes this minimum, right? So given that he knows what Min is going to do, and given that he knows that Min is going to act in a way that is sort of contrary to his own interests, Max should play the strategy that maximizes the minimum. Okay, is that clear? So there's this, if we're thinking about what Max should do, there's this nested optimization, this max-min term. He should play the strategy that maximizes the minimum over Min's two actions. Okay, now things are symmetric for Min, of course. We've been thinking so far about the situation in which Max has been handicapped and is forced to reveal his strategy to Min and let her best respond. But what if the tables were turned, right? Like if Min was the one who was under this handicap, was forced to reveal her strategy to Max and let Max best respond, then she could go through an equivalent chain of logic. She could say, well, look, whatever strategy I announce that puts probability Q on morality, I can figure out what is the expected utility that Max is going to get if he plays economy and if he plays society. And I know that if he gets to best respond, he's going to pick the action among those two that maximizes his utility. I'd like his utility to be as small as possible, so I should pick the Q that minimizes that maximum. Okay, so if Max goes first, he should solve this max-min optimization problem. And if Min goes first, she should solve this min-max optimization problem. Okay. So let's, just to get a better sense of this, again, this particular toy game, let's maybe go through this exercise of figuring out what Min should do, what Max should do, and how much of a disadvantage it is to have to go first. Right, so it's sort of clear if you think about it, that in a zero-sum game, like going first is definitely only a disadvantage. It can't be an advantage, because what you're doing is you're revealing information to your opponent that they wouldn't have otherwise, that they can use to try to harm you, right? Their only goal is to minimize your utility. And so whatever they would do if they got to go first, they could still do it if they get to go second, but maybe they could do something even more clever that would harm your utility even more if they have knowledge of what you're doing, right? So giving up your strategy, revealing your strategy can only be a disadvantage. But, it's not clear how much of a disadvantage it is. Let's see, let's work it out in this case. Okay. Maybe one sort of thing worth noting. So if you look at the payoff that, or the cost, let's say, that Min has for playing morality, it is increasing in P, the weight that Max puts on economy. If Min plays morality, then the payoff that she gets is increasing in the weight that Max puts on economy, because the payoff for economy is positive and the payoff for society is negative. Similarly, if Min plays tax cuts, then the payoff she gets is decreasing in P, the weight that Max puts on economy, because the payoff when Max plays economy is negative, and when he plays society, it's positive. And so if we sort of imagine plotting out as a line the payoff that Min gets, or the cost that Min experiences if Max, as a function of the weight that Max puts on economy, this line has positive slope. And if we imagine plotting out as a line the payoff that Min gets, the cost that Min experiences as a function of the weight that Max puts on economy, this line has negative slope. Okay, now Max is going to pick a point on the x-axis. Let's say that the x-axis here is P. Okay, Max is going to pick a point on the x-axis, and Min is going to play whichever of these two lines is below the other one. She's going to pick the action that minimizes the cost. And Max would like to maximize the height of the point she ultimately picks. So knowing this, geometrically on this plot, which point P should Max pick?
The intersection?
She should pick the intersection, right? He should pick the intersection, because if I plot out the maximum of these two lines, right? The maximum is sort of like this upper envelope up here. And so the maximum is minimized here at exactly the intersection. Okay. So Max would like to maximize the minimum payoff of these sort of two curves here. He should pick the P that causes them to intersect. He should sort of randomize between economy and society exactly in the proportion that would cause Min to be indifferent between her two actions. Okay, so this makes Max's computation very easy, right? Like, he knows that Min's payoff for playing morality, if he plays economy with probability P, is exactly 3P minus 2 times 1 minus P. And he knows that her cost for playing text cuts is exactly P times minus 1 plus 1 minus P. And so if he wants to minimize or maximize the minimum of those two, he should pick the P that causes these two expressions to be exactly equal. Okay, so it's just a little bit of algebra. And when you work out the algebra, Max would figure out, okay, he's supposed to, the thing he should do if he has to sort of play defensively like this, if he has to go first, reveal his strategy and play defensively so that things are as good as possible for him when Min best responds. In this case, he should focus on the economy with probability 3/7. Okay, and of course, he has to put the remaining probability 4/7 on society, and so we have a mixed strategy for Max here. Now, this mixed strategy is designed so that Min is exactly indifferent between her two actions. She's exactly indifferent between playing morality or text cuts. And so we can work out that the payoff that Max will get when Min best responds is, well, it doesn't matter what she plays when she best responds. We work things out so that no matter how she plays, the outcome is the same, and it's 1/7. Okay, so just to sort of like remember, not that the number is like deeply important, but like in this particular example, when we put Max at a disadvantage and forced him to reveal his strategy, but then Max played optimally, he could still guarantee himself payoff at least 1/7. Okay, he gets payoff 1/7 here when he is in the position of disadvantage. So let's think now about how much better he can do if we put him in the position of advantage, if we make Min go first and give Max the opportunity to best respond, right? Like, things should only be better for him. So his payoff should be, like at least 1/7 and maybe better. So again, like the computation, the logic that Min goes through should be exactly the same as Max went through a moment ago. We've got these two curves representing the payoff that Max gets as a function of the probability that Min puts on one of her actions, say morality. And the payoff curves for these two options Max has have opposite slopes. And Max is going to pick the alternative that maximizes his payoff. And Min would like to make that as small as possible. And once again, the maximum is minimized exactly at the point at which the two curves intersect. And so, like, Min can, just as Max did, think to herself, okay, well, I should put weight on morality Q exactly such that my mixed strategy Q and 1 minus Q makes Max exactly indifferent between his two actions, right? So we can write down, as a function of Q, what is Max's payoff for focusing on the economy? It's 3Q minus 1 minus Q. And we can write down what is his payoff for focusing on the social contract. It's minus 2 times Q plus 1 minus Q. And Min is looking for the value of Q that equalizes these two. The line of algebra, she can work it out. It's 2/7. She should focus on morality 2/7 of the time. Okay, so Min has some other mixed strategy. If she is in the position of disadvantage, she should focus on morality 2/7 of the time and tax cuts 5/7 of the time. once again, when Max best responds, well, it doesn't really matter what he does. Min has rigged things up explicitly so that Max is indifferent between his two actions. His chance of winning the election is exactly the same, no matter which of economy or society Max focuses on. That's sort of a characteristic of Min's defensive strategy here. And when Max best responds, his payoff is, again, we can work out 1/7. Okay, so something a little interesting happened here. When we put Max at the position of disadvantage, of having to go first, but allowed him to play optimally, we found that despite being in this position of disadvantage, he could get himself payoff 1/7, but that even when he was in the position of advantage of knowing Min's strategy ahead of time and getting to best respond, he still couldn't do any better than 1/7. Right, so in this case, although of course it wasn't a disadvantage to go first, it wasn't really an advantage either. Okay. So yeah, so I want to think about this and think about whether this is a quirk of this game or whether this happens more generally, and what the implications of this are. So these strategies that we computed for Min and Max, right? We're sort of not, we weren't thinking like equilibrium-like thoughts. We weren't thinking, okay, what's a stable state that we might both find ourselves in? We were thinking sort of defensive play thoughts, because normally when we think about playing in a matrix game like this, we think about what happens when both players play simultaneously. And remember, equilibrium, of course, is a state in which both players are simultaneously best responding to the other. But when we derived that Max should play 3/7, 4/7, we were thinking about how Max should sort of play defensively in this sequential interaction where first he had to reveal his strategy and Min got to best respond. And when we derived that Min should play 2/7, 5/7, this was again in this sort of defensive sequential situation where, Min was thinking what she should do if she first had to reveal her strategy and allowed Max to best respond. Right, so there was no thinking there that Min would, we knew that Max would best respond to what Min did in that situation, but there was no thinking that Min should also be best responding to what Max did, because Max got to move after Min. Okay, but because the payoff for both players was 1/7, regardless of whether they moved first in this interaction or whether they moved second, actually in this game, it must be that this pair of strategies that we derived in this defensive manner, 3/7, 4/7 for Max and 2/7, 5/7 for Min, is actually a Nash equilibrium of the game in which both players get payoff 1/7. And the reason is because, we know that when Max plays according to this, that Min can force the cost to be 1/7 even when she is best responding. And she can't do better than that because she's best responding. Similarly, when Min commits to this strategy, 2/7, 5/7, Max can force the payoff to be at least 1/7, even when he's best responding. And of course, he can't do better than that because he's best responding. So when both players are playing these strategies and simultaneously getting payoff 1/7, they must be both simultaneously best responding to each other's strategies. Okay, so one thing to observe is the fact that in this game, the payoffs turned out to be equal, independent of the order of play, meant that by computing these strategies in this sort of defensive sequential way, which was sort of easier than computing strategies, equilibrium strategies in general. There was no circularity here the way there normally is in equilibrium computation. We were just sort of computing, like 2 steps of rational thought. It meant that like we were actually computing Nash equilibria of the game. So that's one thing to notice. And so like let's maybe investigate further and see if this is a more general phenomena that happens in zero-sum games. Okay, so so far we sort of talked very concretely about a particular zero-sum game. The next part of the lecture, I'm gonna jump into abstraction and prove a theorem about like general zero-sum games. So let me pause here to ask if there's any questions about anything we've talked about so far, because it is a good time to ask questions, because so far we've talked about very concrete things, very concrete calculations, but it's going to get more abstract soon. So let's make sure we all are on the same page. So any questions? Okay. Cool. So like that was a very simple example of a zero-sum game. Each player only had 2 actions, and so we could think of their mixed strategies just as being defined by single numbers p and q. But more generally, a 2-player zero-sum game could have a bunch of strategies. Let's say that let's use n to denote something that might be the number of actions available to a player in a zero-sum game. So when I write n in brackets like this, I mean this as shorthand for the set of all actions 1 through n. Okay. And similarly, when I write delta of n like this, what I mean is the set of all probability distributions over those actions. Okay. And so let's now think of an arbitrary 2-player zero-sum game in which the row player has n actions and the column player has m actions. Okay, and remember, we can always represent such a zero-sum game as an n by m matrix that I'll call U. Okay, and you can think about the entry, the ijth entry, the entry in this matrix corresponding to row I and column J. You can think about that as the utility that Max, the row player, will get if he plays I and Min plays J. Okay, and we only need one. The reason we can think about a matrix instead of these sort of more general games that like in which in each entry there's like a tuple of payoffs, 1 for each player, is because in a zero-sum game we only need 1 number. We know that Max wants to maximize that 1 number and Min would like to minimize it. Okay, so we can think of a zero-sum game, a general zero-sum game, as being represented by some n by m matrix, where n is the number of actions available to the row player, 1 for each row, and m is the number of actions available to the column player. And given such a game, we can define what I'll call the max-min value of the game and the min-max value of the game. Exactly sort of analogously to how we thought of these things in the presidential election game. Okay, like in Word, I'll sort of say it in English and we'll sort of go through the math. In words, the max-min value of the game is the payoff that Max can guarantee himself if he is handicapped so that he has to go first and announce his strategy, and Min is able to best respond. And the min-max value of the game is conversely the value of the game that Max can guarantee himself if Min is the one who's handicapped and has to announce her strategy first, and then Max has the ability to best respond. Okay, so let's just walk through this. The max min value of the game, remember this is the payoff that Max can guarantee himself if he's forced to go first. That's why the max is sort of on the outside here. Max is the player who's going first. So Max is gonna announce some mixed strategy to Min. Okay, so he'd like to choose the mixed strategy that will maximize his payoff after Min best responds. So he's going to choose some distribution over his n actions, and he'd like to choose the distribution that maximizes whatever comes next. Now what comes next? Well, next Min gets to best respond, and she's going to choose the action of hers, y, that minimizes Max's expected utility given her choice. Okay, so for each action y she could choose, Max's expected utility is just the average over all of the actions that Max could play, of the probability that he plays that action, of the utility that he gets when he plays that action and when Min plays y. And right, so the inner expression here is just the expected utility when Max plays this mixed strategy P and Min plays this pure strategy Y. And what Min is going to do is she's going to pick the action, the pure strategy that minimizes the expected payoff. Okay, and so Max would like to pick the mixed strategy that maximizes the payoff after Min minimizes, if Max is going first. Similarly, the min-max value of the game is the value that Min can sort of force if she's handicapped and has to go first. So she would like to pick the distribution over her actions, the distribution Q over her M actions, such that after Max gets to go second and best respond and choose the action that maximizes his expected payoff, with knowledge of Min's mixed strategy, that the resulting payoff is minimized. Okay, so let me pause here and ask if this is clear, because there's like some, like notational burden here, but I think the idea is sort of pretty simple and intuitive, especially after we've gone through this presidential election game. It's just sort of, each of these is sort of like a two-level optimization, sort of, thinking one step ahead of what your opponent is going to do. I'd like to choose the action that gives me the sort of best payoff if I'm Max, that maximizes my payoff after Min gets to best respond and vice versa. Okay, is it clear what the max-min value of the game is and what the min-max value is, and how this sort of generalizes our discussion of the presidential election game? Okay. Okay, so remember, I think this is hopefully intuitively clear, and it's a couple of lines of math if you want to work it out. It's a good exercise that in a zero-sum game, going first cannot possibly be an advantage. And the reason is pretty intuitive. It's that your opponent just wants to minimize your utility. And by telling them your strategy, you're not removing anything from their strategy space. You're not making it so that so that they can't do anything they would have done without that knowledge, but you're giving them additional information that they can choose to optimize using if it's useful, but they don't have to, right? So like giving them additional information isn't going to harm their optimization, can't make their optimization problem less favorable to them, and it could, because they can always ignore it, and it could make it more favorable. Okay, so just sort of writing that observation down in the notation we just established, what this says is for any zero-sum game U, the min-max value of the game can only be larger than the max-min value of the game, right? Because going first being on the outside of this optimization procedure, right? Max goes first if he's solving the max-min problem. Going first can only be a disadvantage, and max would like payoff to be higher, so the max-min value can only be smaller than the min-max value. Okay, is that clear? Now, like this basic fact about zero-sum games, which is called von Neumann's min-max theorem, the interesting part of it is the other direction of this inequality, right? Sort of like straightforward that going first cannot be an advantage. But what the min-max theorem says is that in a zero-sum game, going first is actually not a disadvantage either. The presidential election game wasn't like unusual in this respect. This is true of all zero-sum games. No matter what the order of play is, whether min has to go first or whether max has to go first, the payoff they can obtain if they play optimally is the same. The min-max value is equal to the max-min value. And so there's a couple of interesting corollaries of this theorem, which we're gonna prove the theorem in a moment. It's like, first of all, it must be that in any Nash equilibrium of a zero-sum game, max must be playing a max-min strategy. In fact, any max-min strategy will suffice. And min must be playing a min-max strategy. Any min-max strategy will suffice. Right, and so this is sort of immediate, but like, if this weren't the case, right, it would sort of mean that there was an advantage, right? If this weren't the case, then it would mean that I could sort of break out of equilibrium by committing to something and going first. And my opponent wouldn't currently be best responding to it. But I can't do that because the min-max value is equal to the max-min value. And one interesting thing about this is that in general, thinking about equilibrium strategies and computing them in general, it seems tricky, right? Because it involves this sort of circular counterfactual reasoning, right? Like I want to play something that's a best response given what my opponent is going to do, but I need to think about what my opponent is going to do in order to make that a sensible optimization goal. But they need to think about what I'm going to do, right? So in general, Nash equilibria have this sort of fixed point feel to them. And there's this sort of circular counterfactual counter speculation that I need to engage in. I need to think about, what would my opponent do given what I'm going to do, but to figure out what I'm going to do, I need to think about what they're going to do, and back and forth. But we didn't need to do that to compute min-max and max-min strategies in the presidential election game, or more generally in any zero-sum game. We just needed to solve 2 steps of optimization, right? We needed to compute basically min's best response problem, right? We needed to solve just a best response optimization, and then max's outer optimization as a function of what min was going to do. Okay, so somehow this makes zero-sum games a little bit easier to think about. And it also means that because there's this thing called the value of a zero-sum game, the min-max value, which is the same as the max-min value, it must be that at every Nash equilibrium of a zero-sum game, I will have the same payoff, right? My value for the game, which is not in general true of other games, right? In other games, we've sort of thought about already, I might prefer one equilibrium over another. The equilibrium might have very different payoff for me, but that can't happen in a zero-sum game. Okay, so let's just like note that these things are not in general true of general sum games, like in the Bach and Stravinsky, little toy example we went through early in the class. I prefer the Bach equilibrium to the Stravinsky equilibrium, and my wife prefers the opposite, right? So that's like the kind of phenomena that cannot happen in a zero-sum game because of the Minimax theorem. It means zero-sum games are easier to play than general sum games. There's no need to engage in counter speculation. You just have to think about playing defensively. And one thing I want to note, just because we're going to give such a slick proof of this, is that the theorem is not at all obvious. So von Neumann first proved this theorem in 1928, and he wrote, as far as I can see, there could be no theory of games without this theorem. I thought there was nothing worth publishing until the Minimax theorem was proved. And Borel, who was another smart fellow, thought that he'd proved the special case for 5x5 matrices and thought it was false for larger matrices. Okay. And in general, this is, what we're going to prove is sort of equivalent to something called linear programming duality, which has lots of important implications. But anyways, the reason that Borel and von Neumann had to work so hard at this is because they didn't know about the polynomial weights algorithm. So the fact that we have studied and derived the polynomial weights algorithm is going to make our lives easy. And sort of, I think seeing how the proof works will also help us appreciate what the polynomial weights algorithm is doing. There's some sense in which the polynomial weights algorithm is a constructive version of the Minimax theorem. Okay, so let's prove it.
Wait, I have a quick question.
Yes.
This is only for 2-player zero-sum games, or like?
This is only for 2-player zero-sum games. Yeah, like this is a good question. Next class, we will think about what happens if there's more than 2 players. Yeah, it's worth thinking about. Like, how much of what we're talking about for 2-player zero-sum games is true for n-player zero-sum games, if any of it. We'll talk about that next class, but yeah, it might be illuminating to just sort of think about it when you're falling asleep. Okay, so let's prove this. Okay, so we want to prove that the min-max value is actually equal to the max-min value. And the interesting part of that proof is showing that the max-min value is at least the min-max value, right? This direction is sort of immediate, that sort of revealing information to your enemy is never a good idea. Okay, so suppose it were false. Suppose the min-max theorem were not true. That would mean that there actually was some game U for which it really was a disadvantage to reveal your strategy to your opponent. Okay, in particular, it would mean that the min-max value of the game, how much Max could guarantee if he got to go second, like actually was strictly larger than the max-min value of the game, like how well he could do if he was forced to go first. And so in particular, we could give names to these numbers. We could say, look, the min-max value of the game, like how much Max can guarantee if he has the privilege of going second, let's call that V1. And the max-min value of the game, like how much Max can get if he's disadvantaged and has to go first, we'll call that V2. And the assumption that the min-max value is strictly bigger than the max-min value, that's sort of like saying, well, V1 is equal to V2 plus epsilon for some value of epsilon that is like strictly bigger than 0. Like V1 actually is bigger than V2 by some amount. Okay, so like, yeah, setting up like a proof by contradiction, if the theorem were false, there would be some game U, there would be some value V1 strictly bigger than v2, such that if min has to go first, then max can guarantee himself payoff at least v1. But if max is forced to go first, then he can guarantee himself payoff only v2, which is strictly smaller. And so, this theorem, it's like, in some sense, just like a statement about matrices, right? Like there's no time, there's no dynamics, there's no time aspect to the theorem. But nevertheless, like the way I want to prove the theorem is by conducting a thought experiment in which min and max are repeatedly playing against each other in this game U. Think about in this thought experiment as play proceeding according to some dynamic, just like we thought about when we thought about best response dynamics in congestion games. Okay, so in the thought experiment, there is time. And here's how min and max are going to play. So min is going to play this game using the polynomial weights algorithm that we derived last class. Okay, so what does that mean? Remember how the polynomial weights algorithm works. It maintains weights across these different actions. We're going to associate the actions in min's copy of the polynomial weights algorithm with like min's actual actions in the game. Okay, so min has m actions. She will run the polynomial weights algorithm by initializing m weights. Every day, the polynomial weights algorithm maintains a probability distribution over these actions. That will be min's mixed strategy at that round, which she will play. And then max will do something, and that will lead to some cost for each of min's actions. Okay, just like the cost specified by the game matrix, given what max played. And that'll be the cost that we feed to the polynomial weights algorithm for each action to update the weights for the next day. Okay, so let me just make sure that sort of this is a sensible thing to everybody, that I can talk about min playing a game using the polynomial weights algorithm to determine what her mixed strategy is. Is that clear? Okay, so min is going to play the game using the polynomial weights algorithm. And what's max going to do? Well, every day, max is going to look at what the polynomial weights algorithm is doing. It's not a secret, right? Like he can just look up the lecture notes from last class, and he knows what the history of play has been so far. So he knows exactly what probability distribution the polynomial weights algorithm is suggesting that min play every day. And max will do the very natural thing of best responding to it every day. Okay, so what max is going to do every day is just best respond to min's strategy. I mean, said another way, if WT is the mixed strategy maintained by the polynomial weights algorithm at weight t, at day t, then max is just going to play the action that maximizes his expected utility given min's mixed strategy. Okay, so this is I'm sort of laying out some dynamic. I've told you what both players are going to do at every round. Every round, min will look at the history of play up until now. She will use the polynomial weights algorithm to define a mixed strategy, and she will play that. Max will best respond to that mixed strategy, and they will do this over a sequence of t rounds. Okay, so this is some well-defined dynamic that we can think about. Are there questions about this thought experiment, like what it is we are thinking about? Okay, so what I want to focus on is what we know about each player's average payoff as they interact in this play dynamic over time. And let's start with min, because we just finished last class deriving the guarantees of the polynomial weights algorithm, so we know something about what min is going to be promised. Right, so First of all, like we can just write out syntactically what is the expected cost to min over time. Well, it's just the average over the t steps of this interaction of the expected utility when min plays according to her mixed strategy and max best responds. And remember what the polynomial weights algorithm promises. Remember, these utilities just correspond now to the losses experienced by each of min's actions. And remember, the polynomial weights algorithm promises that min's actual realized average utility will be no more than the average utility of whatever turns out to be the best action in hindsight, the minimum cost action in hindsight, plus some like regret term that goes to 0. Okay, so what is the best action in hindsight? Well, after t days, when we actually see what action max has played at each day t, xt, we can ask, well, what is the action that min has in hindsight that would have minimized her expected cumulative cost, her expected average cost, given what max actually did? And that's the best action in hindsight. And so what the polynomial weights algorithm promises is that min's realized average utility is no more than the average utility of her best action in hindsight, plus some regret term. Okay, and we can sort of manipulate this a little bit, right? Like, okay, like we're taking the minimum over all of min's actions in hindsight, inside of this average, but like, we might as well have taken it outside of the average. So I can just write this just by sort of moving the min outside as the action that minimizes the utility averaged over the t rounds like this. And syntactically, right, I can notice that this is an expectation, right? It's like an average over t things, my utility at round little t for each round little t ranging from 1 to big T, just a uniform average. And so I can think about this as the utility that min would get playing the action y star against the mixed strategy for max that happens to put weight 1 over t on each of the actions xt. Okay, which I'll just call x bar. So just because syntax can be confusing, let me say this again, because really mathematically nothing has happened here, but there's sort of an important change in perspective. Okay, so what the polynomial weights algorithm promises is something about sequences of play. It says if you play the polynomial weights algorithm for t rounds in sequence, then your average utility over those t rounds is no more than the average utility of the best action in hindsight over those t rounds. And all we're doing in this last step is we're sort of noticing that for any particular action y star, my average utility for playing y star over t rounds is the same thing as saying my expected utility for playing y star when my opponent is playing a mixed strategy that just randomizes uniformly over the actions that she played over the last t round. Okay. And all throughout here, delta t, it's just the regret bound of the polynomial weights algorithm, this thing that we proved we can drive arbitrarily close to 0 by just playing for long enough. Okay, looks something like this. Okay, so any questions about this so far? Basically, all we've done so far is we've remembered the promise of the polynomial weights algorithm. It says that if I play a game with the polynomial weights algorithm, my expected cost is no worse than the expected cost of the best action in hindsight. And we've sort of said, okay, that turns out to just be another way of saying my expected cost is no worse than the cost of my best response against the mixed strategy that corresponds to my opponent playing uniformly at random according to their play history. But if we look at what we've transformed this into at the end, right, like the payoff that I get by best responding to a mixed strategy of my opponents, the payoff that Min gets, that's only smaller than the payoff she would get by best responding to the worst possible mixed strategy her opponent could play, right? That's the max min value of the game. Okay, and we gave a name to the max min value of the game, that was V2. And so what we get is that if Min plays according to the polynomial weights algorithm, then the expected payoff in this game is upper bounded by V2, the max min value of the game, plus this regret term delta t. Okay, and the reason is because, well, the max min value is sort of how much Min can guarantee if she gets to go second, and getting to go second is like having the opportunity to play the best action in hindsight after you know what your opponent is doing, and that's exactly what the max min value of the game is, and it's what the polynomial weights algorithm promises, right? That you're competitive with how well you could have done had you gotten to go second. On the other hand, right, since we've just thought about the average payoff of the game over time by taking the perspective of Min and thinking about what the polynomial weights algorithm requires. On the other hand, we can analyze exactly the same quantity, but taking Max's perspective. Okay, so it's even simpler from Max's perspective. Max is literally just best responding to Min's mixed strategy every day, right? So Max is literally in the position of getting to know what Min's strategy is every day and best responding to it. And so in particular, like he's getting every day at least the min-max value of the game, because the min-max value of the game is a bound on how well he can do if he gets to go second, and we've set things up so that he does get to go second. So because Max is literally getting to best respond to Min's mixed strategy every day, we also know that every single day he is getting utility at least V1. And so in particular, the average utility has to be at least V1. Okay. So on the one hand, the average utility is at least V1. That's because Max is best responding. On the other hand, the average utility over this thought experiment is at most V2 plus delta t, because Min is playing according to the polynomial weights algorithm. And remembering that V1, we've assumed, is equal to V2 plus epsilon, this means, in order for this to be true, it's got to be that epsilon is less than delta of t, the regret bound for this algorithm, for polynomial weights. But delta t is this expression that goes to 0 as t grows large, right? It goes to 0 at a rate of 1 over root t. And this is our thought experiment. So whatever epsilon is, we've assumed that there's like some concrete epsilon bounded away from 0. Whatever epsilon is, we can just take t large enough so that the regret term is smaller than it. And that leads to a contradiction and proves the minimax theorem. Okay, so let me just take a moment to reflect. So in a very strong sense, the polynomial weights algorithm really is sort of a constructive version of the minimax theorem. That's why the minimax theorem follows so directly from once we know the polynomial weights algorithm, because it allows you to be in a position of playing first, right? Like in this thought experiment, Min was playing first, was announcing that she was using the polynomial weights algorithm, and Max was best responding to that. And yet, it guarantees that you could do as well as you could have if you had gone second, right? Because the promise of the polynomial weights algorithm is about doing as well as the best fixed strategy in hindsight. In hindsight means after you've observed what actually happened, right? So like doing as well as the best fixed strategy in hindsight means really doing as well as if you had gotten to observe everything and then go second. Okay, so you can play first, but do as well as if you had played second. That's really what the min-max theorem is about. If you think about the proof, also, it means that it's a pretty good idea to play the polynomial weights algorithm in a zero-sum game, right? Because I'm always going to do as well as if I got to go second, no matter what my opponents are doing. Okay, so even if I don't know very much about the game, right? Maybe I don't even know the whole game matrix. Yeah, I'm just getting enough feedback to play the polynomial weights algorithm, which is just sort of what are my payoffs given what my opponent actually did. It promises me that I always get my value for the game, sort of my safety value that I could have obtained had I known the whole game and sort of optimized defensively against my opponent, no matter what they do. And I might be able to do better. In fact, I'll do as well as if I was in the position of getting to best respond with full knowledge for what my opponent was going to do. So it sort of means that even if you know very little about the game, you can always sort of get the payoff you would have had you played optimally using the polynomial weights algorithm, at least if you're in a zero-sum game. Okay, and it is able to do this again, like without knowing much about the game, right? Like if you think about, let's say a zero-sum game in which each player has n actions. The game is defined by n squared numbers, right? Like for every choice of the row player, for every choice of the column player, there's a number in there. But the convergence bound of the polynomial weights algorithm depends only logarithmically on n. So it means that you can get within epsilon of the value of the game, of sort of playing, of how well you could have done had you studied the game and played completely optimally, after only about log n many rounds, after which you've only really seen a tiny fraction of this payoff matrix, right? Like, because to run the polynomial weights algorithm, you only need to see the sort of rows of the payoff matrix corresponding to the actions your opponent actually played. Okay, so somehow, like, the polynomial weights algorithm allows you to learn to play optimally in a zero-sum game without having even really seen most of what defines the game. Okay. So with that and the last of my remaining voice, let's end it there. Hopefully by Thursday, I'm healthy enough to do this in person. See you guys next time.
Thank you, Professor.
Thank you.
Yeah, thanks for coming.
Thank you.